So this is going to be video number 2 on chemical equilibrium, and here we're going to talk about equilibrium calculations. So there's two types of calculations that I can give you. I can give you concentration data or concentrations and ask you to find Kc or Kp. Okay? Or I can give you Kc and Kp and ask you to find the equilibrium concentrations. Okay, we'll work a problem of the first type first. All right, so we're going to look at the equilibrium between H2 and I2 to make 2HI. Right, so we're going to start with 2/10 of a mole of H2 and 2/10 of a mole of I2. So we're starting with H2, HI, and no HI. Okay. 2/10 of a mole here, 2/10 of a mole here. Nothing about HI is mentioned, so we're not starting with any of this. So at equilibrium, it was determined that I2 had that I2 is 0.020 molar, and we want to find Kc for this reaction. Okay. Now, when you work a problem like this, you're given two pieces of information. You're given initial concentrations, either the initial concentrations or the initial number of moles. Here he gave you the initial number of moles. Okay, but there's one more piece of information that you have to have. You have to know the concentration of one of the species at equilibrium. And from that, you calculate the others. And so, in this case, that was the iodine. We allowed the system to come to equilibrium. We went in and measured the iodine concentration, and that was 0.020 molar. So one more time, you have the initial concentrations or initial number of moles, and you have the number of moles or concentration of one species at equilibrium. Okay, so the first thing I'm going to do here is take these initial number of moles and convert them to a concentration. All right, so that 2/10 of a mole of I2, we divide it by the 2 liters, right, to get a concentration of 1.00 molar, right? Molarity is moles per liter. And we do the same calculation for I2, 0.2 moles divided by 2 liters is 0.1 molar. So why am I doing this? Because these are moles. Look carefully at the problem. These are moles, and this is molarity, which is concentration. We can't mix and match. Now, we can do the problem off the number of moles, or we could do it off the concentration, but we can't mix and match. So everything has to be moles, or everything has to be molarity. And in the end, you're going to have to, you could work it off moles, but at the end you will have to convert it into concentration to get the final equilibrium constant. So it's easier to just do it from concentration. So convert the number of moles into a concentration. Okay. So now we note that I2 had decreased, the concentration of I2 had decreased by 0.080. In other words, we started with the 1/10 of a mole, or the starting concentration was a 1/10 of a mole, and the finishing was 0.02. So the concentration changed by 0.080. Okay. So now we know that you have one I2 used for every one, or one H2 used rather, for every one I2 used. Well, you know that. Look at the reaction. H2 plus I2 makes 2HI. That's coming from the balancing coefficients in the equation. If you don't see a number here, the 1 is implied. So basically then, if this went down by 0.0, or if this went down by 0.02, or by 0.08 rather, then this went down by 0.08. Remember that reactions do not create matter. You can't have matter, coming out of thin air. All chemical reactions do is rearrange the matter that's already present. So if these go down, then this goes up, and vice versa. So if this went down, and these two are going to go down by the same number. All this comes from the balancing coefficients in the equation. So if the concentration of I2 drops by 0.08, then H2 also drops by 0.08. All right. So what is the equilibrium concentration of H2? 0.1 minus 0.08, which is 0.02 molar. Okay, now, what about the concentration of HI? Okay, we have 2 moles of HI formed for every mole of I2 consumed, right? Where's that coming from? One more time, it's coming from the coefficients in the balanced equation. For every one of these we lose, we make 2 of these, right? Yeah, so you have 2 moles of HI formed for every mole of I2 consumed. So what's our equilibrium concentration of HI? It's going to be twice the 0.08. I2 went down by 0.08. HI goes up by 2 times 0.08, or 0.160. Okay. So now we summarize all this into what's called an ICE table, which stands for initial, change, and equilibrium. Okay, so initially we had 1/10 of a mole after we converted it into a concentration. The concentration of H2 is 0.1, and concentration of I2 is 0.1, and HI was 0. Okay, we didn't start with any HI. So one more time, in a problem like this, you're given the initial concentration, and then you're given the concentration of one species at equilibrium. In this case, it was the I2. Okay, so we said if the I2 started at 0.1 and finished at 0.02, that means we lost 0.08. Now, the rest of this comes from the balancing coefficients in the equation. Okay, so if this went down by 0.08, then this went down by 0.08. And if these two went down by 0.08, then this went up by twice that number, which is 0.6. Okay, and so in our very last step then, so this was our initial, this is what we started with, this is our change, okay, and then what are the equilibrium concentrations? You subtract the change from the initial. So 0.08, so 0.1 minus 0.08 is 0.02, okay. Here we add, okay, so our change we lost here and added here. So we started with nothing here, we went up by 0.16, so what's our equilibrium concentration? 0.16. So what's our equilibrium constant then from this data? Concentration of HI squared, coefficients become the exponents, divided by product of the concentrations of H2 and I2. So that's 0.160 squared. That's 0.160 squared divided by 0.02 divided by 0.02. You divide by both of these, or if you like, put brackets or parentheses around that, and that comes out to be 64. Okay, that type of problem is typically pretty simple. One more time, you're given initial concentration data, and you're given the concentration of one species at equilibrium. And you basically have to use the reaction stoichiometry to figure out the equilibrium concentrations of the remaining species. Okay, now let's work another example. Let's work a problem of the second type. Okay, let's work a problem of the second type. So here, we're going to tell you what the equilibrium constant is. And you have to figure out what the equilibrium concentrations are. So we know the reaction is going to shift. It's just a matter of how far it shifts. So we're going to look at the reaction between carbon monoxide and water to make carbon dioxide and hydrogen. Okay, all gases, and this has a Kc of 4.06, equilibrium constant of 4.06 at 500 Celsius. Okay, so if 1/10 of a mole of water vapor and 1/10 of a mole of carbon monoxide are added to a 1 liter container, what will be the concentrations at equilibrium? Now, can you see why it's going to shift? Why is it going to shift? The equilibrium constant is equal to 4.06. So what this means is, at equilibrium, this concentration times this divided by the product of these two divided by the product of those two must equal 4.06. So, but we're not starting with any of these. This is initially, this is 0 and this is 0. So it's going to shift to the right. Okay, it's going to shift to the right. Question is, how far is it going to shift to the right? We don't know. We don't know, but we do know that these are going to go up and these are going to go down until that ratio becomes equal to 4.06. So one more time, the product of these divided by the product of these has to be 4.06 at equilibrium. Clearly that's not starting out. Because what do we have starting out? This times this divided by that times that is 0. So it's going to shift to the right until it becomes equal to 4.06. We don't know how far it's going to shift, but we do know it's all 1 to 1. You don't see any numbers here, so the 1s are implied. So these will go up, and these will go down by the same amount. So we'll let x represent the amount by which the reaction shifts. Right? So we're going to produce X moles of CO2, X moles of H2, and our concentrations of CO and H2O will go down by X. One more time, remember that all chemical reactions do is rearrange the matter that's already present. So if these are going up, that means these have to be going down by the same amount because it's all 1-to-1 stoichiometry. So K is going to be products over reactants, and the coefficients become the exponent. So concentration of CO2 times concentration of H2 divided by the product of these, concentration of CO times H2O. So it's these two are going to be X. Reaction is going to shift. So at equilibrium, these two will be X, and these two will be X, and these two will be 0.1 minus X. Right? So we're going to set this equal to the equilibrium constant and solve it. Okay. So we could do it something like this, and we could say x squared over 0.10 minus x times 0.10 minus x is equal to 4.06. And then we could write this out the long way. So 0.1 times 0.1 minus 0.1x minus 0.1x minus x squared. That would be a nightmare to try to solve it out directly. But there's a trick here. Okay. This right side is a perfect, or I'm sorry, the left side rather is a perfect square. So basically we could take the square root of both sides. In other words, we could rewrite this as x over 0.10 minus x squared and say that's equal to 4.06. Right? We could rewrite this as x divided by 0.10 minus x times x over 0.10 minus x, which is x over 0.10 minus x squared. Now we can simply take the square root of both sides. Okay, so basically then x divided by 0.1 minus x is equal to 2.01, right? What's 2.01? It's the square root of 4.06. Alright, so you take the square root of both sides, so x over 0.1 minus x is equal to the square root of 4.06, which is 2.01. Okay. Now, this should be pretty much of a cinch to solve. Alright, so x is equal to multiply this by 2.01. So x over, in other words, x is equal to 0.201 minus 2.01x. Move this over to the left side to combine our x's. So 3.01x is equal to 0.201, or x is equal to 0.201 over 3.01, which is 0.067, right? So remember the way we set this up. X was the concentrations of CO2 and H2, okay? Because there were none of those present when the reaction started. To get the concentrations, equilibrium concentrations of the reactants, we have to subtract, right? Because the product concentrations go up and the reactant concentrations go down. So 0.10 minus x is 0.10 minus 0.067 is 0.033. All right, so there's a check that you can do. It's always a good idea to check if you can do it, and that's basically to plug all this in and see that it does come out to be 4.06. So we plug in 0.067 times 0.067 divided by 0.033 divided by 0.033, and you get 4.12, which is more than close enough. That's well within any kind of rounding errors. If we'd carried more digits, it would have come out closer, a little bit closer. Okay, now, so that's the second type of problem. Now, I want to do another type, and that's when K is small. Okay, this is another kind of special case. Okay, so let's look at the decomposition of water into hydrogen and oxygen gases. Suppose at 1,000 Celsius, which is a pretty high temperature, what is going to be the hydrogen concentration when the system reaches equilibrium if the constant is 7.38 times 10 to the minus 18. Now I want you to notice that's a very, very, very small equilibrium constant, 7.3 times 10 to the minus 18. Okay, so we know that the concentrations are going to be, even at 1,000 Celsius, are going to be very small. Right? So we're going to set up we're going to set up our ice table, initial change in equilibrium. All right. So we're starting with 1/10 of a mole of water. Okay, we'll assume it's in a 1 liter vessel, so the moles become the concentration. We're not starting with any hydrogen and oxygen, so those are 0. So what's our change going to be? Even as small as it is, because there's no hydrogen and oxygen present, the reaction is going to shift to the right a little bit, even a little bit. We don't know how much it's going to shift, so we'll let X represent that. But now we're not dealing with one-to-one stoichiometry. Okay, it's basically, it's 2 to 2 to 1. So if we let X represent the amount of oxygen that's formed, we'll get 2x moles of hydrogen, and we'll lose 2x moles of water. So that we get 0.1 minus 2x, 2x, and x. Okay, so we plug all this in, and we would basically get this equation, which would be 2x squared times x. That's basically, you could simplify that into basically 4x cubed. Well, that's what I did down here. Times 0.1 minus 2x squared is equal to 7.3 times 10 to the minus 18th. Now, that's a cubic equation. There's no way simply that we could come up with a simple solution for that. Okay. So there's a simplifying assumption that we can make. Okay. Now remember, a small value of K indicates a reaction that favors reactants. Okay, something to the 18th power is a really small equilibrium constant. So we're going to make an approximation, an assumption. We're going to assume that for all practical purposes, that 0.1 minus 2x is equal to 0.1. In other words, what we're going to do is we're going to neglect the effect of the dissociation. We're going to say this x is so small, the amount of the water that we're going to lose is so small that it's actually negligible. Okay, so now our equation that we had set up, which is 4x cubed over 0.1 minus 2x squared, gets simplified down to 4x cubed over 0.10 squared is equal to 7.3 to the minus 18th. Well, now we have something that's really easy to solve, right? So we would cross multiply. In other words, you had 4x cubed over 0.10 squared is equal to, you want to write it all out, 7.3 times 10 to the minus 18th over 1. Anything divided by 1 is the number itself. So now we can cross multiply. This times this is equal to this times this. 0.10 squared rod is 0.01 times 7.3 to the minus 18th is 7.3 to the minus 20th. 7.3 to the minus 20th. So divide by 4 and you get 1.825 times 10 to the minus 20th. Take the cube root of that, and x comes out to be 2.6 times 10 to the minus 7th, which is indeed pretty small. Okay, and the way we set the problem up, the concentration of hydrogen would be twice that, which is 5.2 to the minus 7th. And if we tried to subtract 5.2 times 10 to the minus 7th from 0.1, for all practical purposes, that's 0.1. This number is like 6, 7 orders of magnitude smaller than this number. So it is, in fact, negligible. So you can do this where the equilibrium constant is really, really, really small. You can just assume that the reactant concentration doesn't change. We'll do this a lot in the subsequent chapters when we start getting into acid-base chemistry. It's a very simplifying assumption that you'll do in an equilibrium problem, is to neglect the effect of the dissociation. You can get away with it when the equilibrium constant is really small. Okay, we will stop here.